Hi, welcome. This is the second module of our class 1 for course Fabrication Techniques for MEMS based sensors from clinical perspective. Now, what we have seen until now is there are several sensors, right, that we can make for solving some important problems in the area of medicine or in the area of biomedical engineering. Same technology that we will be discussing in this particular course can also be used for fabricating devices, micro devices to be precise, or devices based on MEMS based technology, that is micro electromechanical systems based technologies, that can also be used for other applications such as electronics, robotics, chemical engineering, mechanical engineering, and so on. So, in our class 1 what we saw are few devices starting from the micro heater, right. So, today what I want is I will just show it to you how the heater pattern looks like. Now, the pattern that I will be showing it to you would be different than what you are looking at the screen, but the idea is that the micro heaters, like I said, can be patterned in a different way because it is nothing but a resistor, right. So, resistor, if you want to have a resistance of a metal, if you want to increase the resistance of a metal, you can increase the length or decrease the area, right. So, let me show you the micro heater which is right now with me. All right. So, if you can see here, right, this is your micro heater, all right, this is a micro heater. You can see the pattern, right, pattern of the micro heater on the glass substrate, right. See, is a pattern of the micro heater on the glass substrate, all right. This is the back side of the heater, back side of the heater. And what we have done, we have used chrome gold, we have used chrome gold as a metal. Okay. So, this is how the micro heater looks like. Now, this again you see that the length is high, the area is also high. So, the resistance would not be that low, but we for this heater was patterned with a particular application. Now, another thing that you may have observed is I am wearing gloves, right. So, to avoid the fingerprints, so to avoid the contamination on the device. Again, these devices are for the demo, and that is why even the recording studio is not a class clean room like class 1000, class 10,000, right. This is just to show you the devices outside the clean room, right. But if you have a complete device, then the devices are of several types. One, that can only be used in a clean room environment. Second, that can only be used anywhere else. So, we have to design the device, since it is a clinical approach, clinical research. These devices should be able to go outside the laboratory, and at the same time it should not have contamination issues. That can be done when you package the complete device, right, because again the clinical environment, the hospital environment would be is considered to be cleaner compared to the dispensary. When I say cleaner, so suppose a surgical room is there, surgery room is there, it is around class 10,000. Okay. So, then what we have seen? We have seen an interdigitated electrodes, right. Then after interdigitated, so in interdigitated electrodes what we have seen, that there is a heater, and on heater there is an insulator on which there are IDE patterns, right. So, if you want to see interdigitated electrodes, I will show it to you. I will show it to you here. Now, if you see here, this one which I am pointing at, this one, all right, this one, this sensor here, this chip has a micro heater at the bottom, and on that there is an insulator on which there are interdigitated electrodes made out of chrome and gold. This particular chip, once again I am showing it to you, this chip, okay, this chip. So, we will see in detail about the fabrication of this chip with a better zooming angle when we are talking about this devices in detail. Right now my idea is to show it to you how it looks like, then we will go into detail how we can fabricate it, at that time we will even zoom it further to understand how it looks like from the actual design point of view. Okay. So, what is the role of that one? The role of that devices was that now on this interdigital electrodes you can load, let us say if I load piezoresistive material, and if I create a diaphragm on the back side. So, what does it mean? I have this electrode, right. So, you see here I have a oxidized silicon wafer. So, I will draw oxide, sorry. Okay. And then I have heater, then I have insulator, then I have interdigitated electrodes. This is what this particular diagram is. All right. Now, if I have piezoresistor or piezoresistive material such as P dot PSS on this, and if I apply a force or a pressure on this piezoresistor, if I apply a force, then it will not show change in resistance, or it will show a very poor change in resistance and very small change in resistance. Why? Because I am using silicon, then I have silicon dioxide, then I have silicon, right, again I have silicon dioxide, I have here heater, right, I have here interdigitated electrodes, right. Not because of these things, because silicon is hard, material. So, if I want to see the bending, if there is a bending, then there is a strain in the piezoresistor, right. For that I had to create a diaphragm. So, what is diaphragm means? That we will etch silicon from back side. In this particular fashion, all right. So, this is your diaphragm that you have created, this is diaphragm that you have created, and now if I apply a force, then diaphragm will bend, and this bending of the diaphragm would cause change in the resistance, You got it. So, if I want to deposit a material which is a piezoresistive material on this particular electrodes, then I have to have a diaphragm on the back side. This can be one of the application. Another application is, instead of piezoresistor, instead of this P dot PSS, right, what I will use? I will use a gas sensing material. So, if this material is material used in sensing, gases, right, such as semiconducting oxide materials, like indium tin oxide, zinc oxide, tin oxide, right, indium oxide, right, tungsten oxide. Then if in the presence of gas, in the presence of VOC, volatile organic compound, there will be change in resistance because of the reducing, because VOCs are reducing gases. We will see detail how we can use it. I am just showing you that the application of this particular device right now can be in many areas, and two of which I have just shown it to you. One can be a force sensor, another can be a gas sensor, right. So, the device that you have seen right now, which I have shown it to you, right, was a micro heater on which there is an insulator on which there are interdigitated electrodes. Then what we have seen? Then we have seen a device for atrial fibrillation. So, again we need a flexible force sensors, right. So, I have to make a flexible force sensors at the tip of the catheter, the tip of the catheter, and I told you that we will discuss in detail atrial fibrillation. So, when you talk about tip of the catheter, then we need again a flexible force sensors, right. So, what should be the sensing material? It can be just a strain gauge. So, if I create a strain gauge or array of strain gauge like this, right, then it can measure force, correct. So, how can I create this array of strain gauge? On flexible material. So, to see the pattern, I have here another wafer, I have another wafer which you will see, how the chip looks like. When the center of this chip there are force sensors, you see here. So, if I show you this one, right, then in the center of this chip there are force sensors, center, okay. When I talk about center of the chip, these are 4 chips, 1, 2, 3 and 4, and the center of the chip there are 4 sensors, alright. So, if I create this kind of pattern, on flexible material, it will be a flexible force sensors, isn't it, right. So, if you just look at me now and you see what I am holding, right, you can also hold the wafer in the way I am holding, it is similar to this, right. Earlier wafer that we had was a micro heater, right. So, there are 2 ways of holding it. When you perform lithography, the best way of holding is always using tweezer. This is called tweezer, alright. So, you can hold with tweezer or you can even hold with the gloves like what I am holding right now. So, you see there is a, so if I put it properly, then you can see the pattern properly, right. So, on one side I have flexible force sensors, a pattern for flexible force sensors that I can use further. On another side I have a heater, this is a heater, this is a pattern for flexible force sensors, right. So, heater we know how we can use it, we now know that how we can use flexible force sensors, right, for the atrial fibrillation, for measuring the catheter contact force, right. So, there are several ways of how people are comfortable by holding the wafer. Again, the best way is to hold with tweezer, alright. Now, depending on the dimension, depending on the primary flat and secondary flat, the wafer can be identified as p type or n type. You see there is a flat, one is primary flat here, secondary flat is at the bottom. So, it is at 90 degree, you see here there is another flat 90 degree primary flat. If I see it is not circular, you see it is not circular wafer, there is a primary flat here and then there is a another flat, let me just show it to you, which is here at the bottom. This is in 90 degree with respect to the primary flat, here is a flat, here is a flat. So, let us try to see if you can catch it. Yes, you see primary flat and secondary flat, right. Secondary flat is always smaller with respect to primary flat. If we know where is the secondary flat with respect to primary flat, then we can understand whether the wafer is 100 or it is 111, whether it is n type or it is p type, alright. This is the advantage of primary flat and secondary flat. We will again see primary flat, secondary flats, we will see how the lithography is done, how you can create this pattern, a lot of other stuff in this particular course. That is the idea of this particular course, to educate the students, right, in the area of microengineering, particularly when we can solve some very interesting problems, right, using these devices. So, then what we have seen? We have seen the flexible force sensor for atrial fibrillation, followed by a cantilever, a piezoresistive cantilever, right. So, when we talk about piezoresistive cantilever, right, I have told you that there is an SU 8 tip that is used for piezoresistive cantilever, and as the name suggests, there is a piezoresistor embedded within the cantilever, piezoresistor embedded or integrated within the cantilever, right. How we can integrate a piezoresistor inside a silicon or on the cantilever, we will see that factors. Now, as we know, if there is a piezoresistor, if I bend this cantilever, if I apply a force, then there will be change in the resistance, there will be change in resistance, right. So, how each cantilever looks like, you see you can see the chip here, right, you can see the chip, but this chip at the end of this chip. So, if I draw just a line like this, and the end of this chip, if you just concentrate on this particular chip, the line that I have drawn is this cantilever. Now, why I have drawn line? Because you cannot see, you cannot see with your naked eye, you have to go for a microscope to understand that there is a cantilever. So, how this chip looks like? Let us see here. I have cantilevers for you. If you can focus on the disk, yes. So, you see or let us do like this, let us focus, I will put in my hand, let us try to focus this, yeah. So, the small things within here, right over here, okay, these chips, these are the chips, these are the chips, but within this chip also, within this chip at the end of the chip there is a cantilever, you guys see. So, it is so small, it is so tiny, super tiny, right, and we cannot see the cantilever coming out, we can only see the chip, we can only see the contacts, that we can take the contacts out of the cantilever. So, it is very difficult, to right now see the cantilever, right, it is very difficult to see the cantilever with a naked eye, even with a zooming factor of the microscope we can see the pattern of the contact pads. That is why if you see the screen, what we are looking at here is, if you see the screen, the contacts that you can see, which one, this chip you can see, and this chip, if I zoom further, what is it? It is like this. You see. So, you can only see this much, you can only see this much, you cannot see this. So, in fact, it is very difficult to see this as well, right, but still you can see. So, what is this? These are contact pads, this one and this one, contact pads, all right. Here is your cantilever that we cannot see, and this is the contact to the cantilever, contact to the cantilever. So, in fact, contact to not only cantilever, but there is a piezoresistor embedded in the cantilever. So, if I zoom it further, if I just say a cantilever, right, and then there are contacts for the cantilever, that is not a correct diagram, right, this is a cantilever and there are contacts for cantilever, then there is a piezoresistor, there is a piezoresistor, and this is the contact to the piezoresistor, this one is contact to the piezoresistor, and then further you go down and make a big contact, further you go down and make a big contact, these contacts are for the cantilever, this one is for the cantilever, the cantilever has a SU 8 tip. So, it is super tiny, as you can see everything is super tiny, right, it is in terms of micrometer. So, you assume that when it is micrometer, if it is like this, if it is nanometer, you can definitely not see with your naked eye, correct. So, and we have seen that this cantilever can be used for understanding the mechanical property of tissue. It can be also used for understanding mechanical property of cells. It can be used to measure the stiffness of the material, right, and we will see how we can fabricate and how we can apply this piezoresistive microcantilever from clinical perspective. All right. So, next was interdigitated electrodes that we have seen, right, and in that what we have seen, if you see the screen, that we can place the tissue and we can measure the change in impedance. Again we will look at this in detail when we go into detail about each devices. Then we have seen this chip, right, this chip, and like I said, now we are interested in measuring the electrical, thermal, mechanical, electrical, thermal and mechanical property of tissue. In this case we should have a sensor that can measure the electrical property of tissue, that can measure the thermal property of tissue, that can measure mechanical property of tissue. And to measure all these three properties, we should have a chip, that consists of or that is integrated with all three sensors, right, sensor 1, sensor 2 and sensor 3. So, this we can call biochip. Why biochip? Because this chip is used for phenotyping or for understanding the change in the tissue properties, and what changes? Electrical changes, mechanical changes and thermal changes of tissue properties. Why it is important, how tissue property changes, why this whole idea of designing this tool comes into picture, and really is it important to make this tool, or because just we know microengineering we are kind of designing different sensors. Lot of questions, right, and it should be there. It should be there before you design any device, before you start working on any device. The main thing is what is the application of the device, what is the gap in the current research that you are going to solve, right. By designing this device, am I going to solve a gap really existing in the technology, or is it really useful from diagnosis point of view, and if yes, how, right. So, always understand the devices from the application point of view. So, first understand the application and understand the problem, and then you devise your design or design your device accordingly, all right. So, if I want to see this biochip, how it looks like, I have a biochip in my hand, right, and here we have to focus on you have to see this area. If I see the camera, yes, now you do not have to see the center, this one, you have to see this one, all right, this one, all three of chips in bottom. You will see there is a subtle difference, because here you can see that there it looks different than this one, right, because now you have a gold pad, and on that you have SU8 pillars, you have gold pad and you have SU8 pillars. If I can show you in this particular fashion, yeah, if you can zoom it further please, yeah. So, you have here, if you see this chip compared to you see this earlier one, we are looking at this chip, right, where it was having micro heater and interdigitated electrodes. Now, we are looking at this particular chip, this 3 in the bottom, and here there is a clear change in the design. You can see very clearly, you cannot clearly understand what are the patterns, but you can see that the chip looks different, and we will see in detail by zooming each chip what are the patterns within the chip. But these are the biochips integrated with 3 sensors, the bottom one, biochips integrated with 3 sensors, this 3 and this one, okay, 4, this 4 integrated with 3 sensors, 1 micro heater, then piezoresistor and then electrodes, all right, and we will see how we can use it, So, if we come back to the slide, what we see here is that we have a heater, we have the interdigitated electrode over which we have piezoresistor, over which we have electrodes, electrode on which there are SU8 pillars, you can see in the center, right, and on the back side there is a etching of the silicon, and this etching is done using bulk micro machining. micro machining, right. If you go to workshop, right, then you machine the things, right, you machine the things. Here we are machining the things at micro scale, at a micro scale, that is why micro machining. Why it is bulk? Because you are removing a bulk of silicon. You see, if this is a silicon wafer, right, if this is a silicon wafer and I am etching the silicon wafer from the back side, this is my silicon dioxide, this is silicon, this is silicon dioxide, and I will tell you why I am drawing such a pattern, always silicon dioxide with silicon. Okay. So, if I say that this silicon, right, is 500 micrometers and I am etching the silicon, I am etching the silicon about 480 micrometers, then the bulk of the material is etched, bulk of the material is etched, right, bulk, and then the diaphragm, this one can be from 1 millimeter, can be from 500 micron, 200 micron, 100 micron, right. This is the window, but this one what I am talking about is this one, the area 100 micron, 200 micron, 300 micron, 400 micron, 500 micron is in micrometers, right. We are performing a micro machining technique, right. So, etching of silicon from back side is done using bulk micro machining. So, if there is a bulk micro machining, then there should be also surface micro machining, surface micro machining, right. So, what do you mean by surface micro machining? How it is different than bulk micro machining? We have to see that as well, and we will see it in some time, all right, we will see it in some time. Now, we will see the bulk micro machining from what is difference between bulk and surface micro machining. Then we have seen microfluidic chip for rapid drug screening, and I have discussed with you why it is important, right. The importance of this particular device that you can see on the screen is that now you can test multiple drugs for the same patient. So, you can load, if I just zoom this particular one, zoom this one, what is it? It is a channel like this connected with a smaller channel, right, channel connected with a smaller channel, and I can load cancer cells in this area. Okay. I can load cancer cells in this area. Now, below this there is the interdigital electrode, here you see here interdigital electrodes. If I zoom further, it looks like this, and below interdigital electrode there is a silicon dioxide, and below silicon dioxide there is a heater. You can see this one, you got it. There is a channel, inside the channel in this area, in this particular area there is an interdigitated electrode which you can see from here. Below interdigital electrode there is an insulator, and below insulator there is a heater. Okay, guys. Now, I have loaded cancer cells in this particular channel, and I am passing a drug, I am passing a drug 1, drug number 1 on this one, right, and I am circulating continuously for some amount of time, let us say 24 to 48 hours. You can select anything, you have to optimize it. Okay. Now, how many channels I have? I have 8 of those. I have 8, 1, 2, 3, 4, 5, 6, 7 and 8, 8 channels I have, right. So, what will happen? I can test 8 different drugs, right, because I have 8 different channels. So, now you can do a drug screening, that means if when the drug is effective, the cells would die and the impedance would change. We will see in detail how these things works. But the idea is, now what you can see? You can see that using this particular device you can test multiple drug for the same patient. That means that if you take these cells from the patient and if you load in this channel and all the remaining 7 channels, right, same patient, and you can try different drugs to see whether drug is effective or not. Alternatively, you can load 8 different patients in 8 different channel and you can try the same drug and see whether drug is effective or not. Both ways it is possible, right. Either same patient, cells from same patient in all 8 channels, you test 8 different drugs, or you take 8 different patients, cells from 8 different patients and you try a same drug and see what is the efficacy of the drug, how the drug is effective to kill the cancer cells or not, right. It is a rapid drug screening device, a rapid drug screening device, right. So, how does this rapid drug screening device looks like? You of course, you can see from the screen, but how exactly it looks like? So, I will just show it to you. I have brought one for you just to see. So, I will put this back and take a tweezer, right, and then we'll pull out this device, right, to show it to you. So, first let us see this device in my hand, right. What you can see is there are certain channels, right, there are number of channels is there, and then below the channel there is in the center there are electrodes, below electrodes there is an insulator, below insulator there is a heater. So, if I show you from the back side, you can see the heater, right, you can see heater clearly, and then you can see that there are lines going right like this, which are interdigitated electrodes. Okay. So, heater is there, but as I am showing from the back because you cannot see clearly from the front, that is why I am showing from the back side. Heater is there on which there is an insulator, on which there is an interdigitated electrode, on which there are channels, and these are 8 different channels. So, you can test 8 different drugs, right. So, let me just show it to you, here, here, right. You can see now. There are channels and then there are contact pads, you can see contact pads right over here, right over here. There are channels and then there is below the channel there are electrodes, below that there is an insulator, you cannot see that, and then there is a heater. So, on the back side let me hold it properly, right. You can see now there is a heater, right, and these lines that are going, lines here, right, on the second side also, these are electrodes, right, and you can see also the holes for the channel, right. This is back side, you can see heater first. When I say back side, from back side you can just see it, there is no metal here. If I touch here, there is no metal, okay, there is no metal on the back side, there is no metal on the back side, right guys. So, we will see in detail again by zooming it further when we are talking about the microfluidic device for rapid drug screening. But in principle this devices can be fabricated using the microengineering technology, right. It can be fabricated using microengineering technology and this can be used for rapid drug screening. So, that was about the microengineering devices. But when you have drug to flow, when you have some fluid to flow in such a channel which is about 1 millimeter or 100 micron or 200 microns, anywhere between 100 to 1 millimeter, right, or 0.5 millimeter, then it comes as a micro channel, and a fluid flowing within the micro channel we have to understand microfluidics. That is why such a devices are also called microfluidic device or microfluidic chips, all right. This devices are also called microfluidic chips. So, when you talk about microfluidic, you have to also understand whether the fluid flowing from that will be a smooth flow or turbulence flow. You have seen, right, those when the river flows, right, unevenly on the stone. If you have seen the river flowing very fast, you will see a lot of turbulence is there. Then you have also seen river which is slow in nature, right, smooth, right, smooth flow, turbulence flow. Same way people who have traveled in flights, right, you may have experienced a air pocket, then suddenly there is a turbulence, right. So, we do not want turbulence, right, we do not want turbulence. So, the flow should be smooth. To understand this turbulence and smooth flow, we should further understand something called Reynolds number. Reynolds number. So, we will discuss this when we will discuss about the microfluidic chip. All right. Now, if I go to the next slide, what I see is I see a device that can be used to understand the antibiotic susceptibility testing. For what? For bacteria. And like we discussed in the last module, that the bacterial antibiotic susceptibility is extremely important problem, since lot of neonates gets affected with several bacterial infections, and the report right now comes in 24 to 48 hours, right, which is too long for a neonate to wait for, and because of this lot of neonate dies, lot of babies dies. That is one thing. Second thing is, even for us, right, even for the grown ups, generally we have to take multiple antibiotics, topical antibiotics, and we do not want to do that, right. We want to create a technology that can aid the doctor to give a particular antibiotic within a shorter period of time, rather than waiting for the reports to come back from path lab in 24 to 48 hours or even sometimes 72 hours. Right. So, for that, can we design a microfluidic chip that can perform this kind of rapid testing, or can we have a just a microchip that can do rapid testing. So, we will see that particular work as well, and for you guys I have also brought you this microfluidic chip. Again we will discuss this microfluidic chip in detail when we are talking about the this particular topic in detail, but right now let us see how it looks like, right. So, in my hand there is a microfluidic chip that can be used to understand the antibiotic resistance, right. This is how chip looks like. Now, again you see this is all about the design, right, and here we have used PDMS. This material is called PDMS, silicon, all right. We will see how we can create this kind of channels, but suppose I want to now commercialize this one, right, and I want to put it in each and every path lab, so that I can rapidly diagnose which bacteria is there, and then rapidly diagnose whether bacteria is resistant to particular antibiotic or not. What should I do? Because the wafer that I am holding right now, right, itself is costly, it is a glass, thin glass, right. I can use a glass slide instead of that, one way. Now, there are gold patterns, and then there is a PDMS. Again you will see that when you want to create a PDMS channels in PDMS, it is a pain, it is not so easy, right, and then it is costly. Suppose we have excellent skills, right, we should have if we have a excellent skill in microfabrication, but if the fabrication is costly, we cannot use this, right, we cannot use this technology. In that case, we have to opt for some different technology. So, instead of creating a channel in PDMS, can I create a channel in plastic? Can I do plastic molding? Can I stick a plastic on this, on the electrodes and heater? Can I make entire device on the plastic, entire device, right? It will solve lot of problem if I have entire device on the plastic, because it will be cheaper, right. It is robust, this is fragile, if I just leave it, it will break into pieces, right. So, the point is that we not only have to design a device, first of course for research we can design a device, we can test the device whether the concept works or not, what we are thinking whether it works or not, it is good for that particular area. Once you have designed the device, it works well, you have to now go further and reduce the price. Now, this is not necessary for every medical technology, for every medical devices, no, right. But for some, yes, when you reach masses where people cannot afford, where people cannot afford the high end technologies for understanding whether they have a particular bacterial infection or not, or something else. This is I am just giving an example. Then if you have a alternative technology which is similar, which gives a similar performance, or which has similar performance to this costly technologies, right, and that everyone can afford. If I make everything in plastic, right, and if I have the total cost of the device around $5, they are about 250 rupees, 300 rupees, then each patient has to just pay 2-3 rupee, 2 to 3 rupee, maybe 5 rupees, maybe 10 rupees, maybe 20, 50, right, but not like 100, not like 300, not like 500, not like 1000. No, we have to try to make technologies, we have to try to design technologies that can reach each and everyone in our society. No one should die because they cannot afford affordable technologies, right. That is the idea, that is the interest, that should be the interest. Either I can create a sophisticated device with and sell it for like few lakhs, or I try to understand the concept, use my research, try to bring the cost down and still maintain the performance, then this device can be used for a common man like you and me and people who cannot afford at all. Right. Can we put this device or such devices in government hospitals, and can it be used for free? Government has lot of subsidies, right. So, you see that if you really understand the concept, you can make technologies which are low cost and which can be used for betterment of human life. All right. Anyway, we will discuss this in detail how it can be used. This is really hot topic and very important topic right now for the in the area of research, antibiotic resistance. Again, when you want to understand any topic, if I talk about drug screening, or if I talk about antibiotic resistance, or if I talk about atrial fibrillation, or if I talk about cancer diagnosis tool, right, every time if I use a word, try to see more, try to look at videos, try to look at the technologies available, try to read research papers. Right. More you read, more you understand how the technologies are or how the technologies work, and how we can create a different technologies compared to the existing technology, right, and how it will be better than what we are creating, right. So, saying that, let us see the next one. Next one what we saw, if you see on the screen, that is the microfluidic chip for evaluating drug efficacy. Right. And here we discuss about that this device we can mimic the in vivo situation on in vitro platform, right. We can mimic the in vivo situations on in vitro platforms, right. These are in vitro microfluidic chip. So, if I want to mimic this one, I can create a device, right, which will have a similar kind of design which is within the body, within the body. This is very simple microfluidic chip. Now, people are also working on organ on chips, organ on chips. So, to have this kind of pattern, if I want to have this kind of pattern, these are all SEM images, like I said, for I am sorry about this, this is like this. So, if I want to have, if I want to create the microfluidic chip, right, I have to have a mold, and this mold is of silicon, and this what you can see, these are all SEM images, scanning electron microscopy, scanning electron microscopy. These are all SEM images, right, and these images are of the mold. And using this mold we will create the PDMS channel, the channels in PDMS. All right. So, how this device looks like? How this device looks like? Let us see. If you see what I have, I will just show you the pattern. I will show you the pattern. See, what I am showing you to you is this one. So, this is the channel that we are looking on the SEM, and then in between the channel, if you see the central region, here we can load the material. On one side we can load the cancer cells, on another side of the channel, here this device there are two channels you can see, right. So, one channel we can load the cancer cell, another channel we can load the epithelial cells or HUVEC cells. HUVEC cells is the right way, HUVEC, HUVEC cells, and in center we can load matrigel, and then we can test different combination of drugs. So, how this works we will see when we are discussing this device into detail. This is the pattern of the device, pattern how the mold would look like. Now, this is just to show it to you how the pattern looks like. This is not a mold again. To create a mold we have to create this kind of pattern on silicon, and then to etch the silicon. To etch the silicon, when you etch the silicon, so opposite of whatever is there in the silicon will come in the channel. Opposite of whatever is there in silicon will come in the channel. If it is too confusing, let us see what do I mean by opposite of that. So, if you see the screen, if I have silicon like this, right, and I create something like this, right, and if I have a PDMS, if I cure PDMS, this layer is PDMS. If I cure PDMS, my PDMS will look like, when I peel it off, when I peel PDMS off, my PDMS will look like this. Do we want this? We do not want this, right. We want channels in PDMS. So, if I take a silicon and if I etch the silicon in this particular fashion, right, then if I pour PDMS, then my PDMS will look like, right, that is that we have created a channel in PDMS, right. This is my PDMS, we have created a channel in PDMS. So, what I mean by opposite is whatever the mold is, this is mold, right, this is mold, whatever the pattern on the mold is, opposite will come here. You see there is a hill here, there is a valley here, there is a valley here, there is a hill here, right. So, you can see here what we have is a valley. So, opposite of that would be hills. If there is a hill which you can see here, right, clearly, then opposite of that would be in the PDMS. That is what I mean by opposite. We will see in detail how we can fabricate this device as well when we talk about the combinational therapy, the devices that can be used for understanding the combination of drugs. Okay. Then we also talked about the flexible MEMS for phenotyping tissue properties, right, and this is similar to that we have seen earlier also. If you see this one, right, or this one, right, it has two sensors, one is electrical sensor and another one is a piezoresistive sensor, and this device looks like this, which we have seen earlier. Just to show you quickly, once again I am showing it to you. This is similar device which I am holding in hand, right. This is the device that you see on the screen as well. This is the device that I am holding right now. This has a piezoresistor and it has a electrode, and everything is in the center, everything is in the center, rest is just a chip, rest just a biochip. Okay. All right. So, that is what we are looking at on the screen, right. It is a on the flexible material, that is why we say it is a flexible MEMS, and can be used to understand the tissue property, that is why we say that the flexible MEMS for phenotyping tissue properties, right. Okay. Now, let us talk about one more technology called immunotherapy, Okay. So, immunotherapy is therapy that will activate your immune system, as the name says, immunotherapy, right. It will work with your immune systems, and again immunotherapy have several divisions. We will just talk about one particular division in which we need to understand whether the immunotherapy drug will be effective or not, right. So, you understand very simple thing here, and then we will discuss in detail later on. Right now, when there is a tumor, which you can see this particular figure, right, and there are cells that flows in the blood vessels, right, then within the cell there are something called T cells. We will discuss about T cells later on, and depending on the tumor, if the immune system is working well, if the immune system responds well to the tumor, then there is a change in CD4 and CD8 concentration, CD4 is to CD8 concentration. Now, you understand this thing, CD8 are called killer cells, this CD4 CD8 are in T cells. Okay. We will see what is T cell, how CD4 CD8 comes. Right now just understand CD8 is killer, CD4 is helper cells. So, what I said, if the immune system responds well to tumor, the killer cells should be higher in number, right, killer cells should be higher in number. So, the blood is taken from the patient and CD4 CD8 ratio is measured using something called flow cytometry. Okay. You understood this much? Now, if I want to create the similar kind of environment, which is my in vivo environment, onto in vitro platform, I can design a microfluidic chip, which will mimic this in vivo situation. Okay. What I will do? Now, I will create the channels and load the tumor in the center of the channel, in the center, like you see here, right. You can see the magnified view of the channel with dimensions in figure number F, right. So, here I will load the tumor, and from here I will pass the T cells, right. Now, immunotherapy is not so easy to understand, but just to help you out, if there is a cancer cell and there is something called immuno checkpoint, right. So, one is called PDL1, alright, and on T cell correspondingly there should be PD1. What is that on cancer cell? PDL1 cancer cell, this is T cell. What is on T cell? PD1. This PD1 will interact with PDL1 and it will think that the cancer is normal, that because normal cells also has PDL1. So, cancer, the T cells cannot distinguish between normal and cancer, In this case, if I block this PD1, then T cells will just kill cancer cells, because it cannot find, it cannot have a bonding between PDL1 and PD1. It cannot have interaction between PDL1 and PD1. So, what will happen? The T cells will start killing the cancer cells, and more T cells will generate, or we can also work on engineering T cells. That is a different topic. Right now we are not interested in that, we are just interested that if I use a drug that can block PD1, and that is why the drug name is called anti-PD1. So, if I block the immuno checkpoint, one of the checkpoints, right, on T cell, and then if T cells cannot have interaction with PDL1, the T cells will kill cancer cell. So, in this case my CD8 will start increasing, killer cells will start increasing. number of CD8 increasing, that means my drug is effective, my drug is effective, right. So, I can use this anti-PD1 and similar kind of drugs, right, and test it by flowing this across this channel loaded with matrigel and tumor. And every time I flow, after 48 hours I measure the CD4 CD8 ratio. That means, I first flow just T cells and measure CD4 CD8, then I flow T cells treated with drug. Let me write down here, T cells treated with drug, T cells treated with drug, and then I again flow in this channel. After 48 hours I again measure CD4 CD8 ratio, correct. Then I try with T cells treated with another drug, 3 drugs, 4 drugs, 5 drugs. Every time I measure CD4 CD8 ratio, I keep on measuring CD4 CD8 ratio. Whichever drug is more effective, I will get a better response for CD4 CD8 ratio, right. That means that you can now, based on the, because see, if there are 3 different drugs, you do not know which drug will be more effective for a particular patient. So, if you know with the help of patient cells, if you pass the if you extract the T cells from blood and you could treat the T cells with drug, you will know whether the patient will respond to particular an immunotherapy drug or not, right. Because you see, if there are 3 drugs, let us say there are 3 FDA approved drugs, and right now we just give one of the drug to the patient, which whether the patient will respond to the drug or not, we probably do not know. So, if we can design a patient centric device, such that you can load the tumor or you can load the cells of the patient in the channel, you extract the blood and from that you extract T cells and you flow T cells without any drug next to this cells, cancer cells or tumor within the microfluidic chip, and you measure CD4 CD8 ratio. Then you treat these T cells with a particular drug, let us say first drug, and you flow it and you measure CD4 CD8 ratio. Then you treat the T cells with second drug and you again flow it in the channel and you measure CD4 CD8 ratio. Then you take T cells, treat it with third drug, right, flow in the channel, again measure CD4 CD8 ratio. If the drug is effective, if the blockage is well, like anti-PD1, right, there are other immunocheckpoints as well. I am just taking example of one immunocheckpoint. Then what will happen? That based on the CD4 CD8 ratio, we can know that yes, look at this result, the patient will respond probably better to this particular drug rather than the another 2 drugs. If you can do that, then you can use this device as a patient centric platform in case of understanding the evaluating the efficacy of the drug, immunotherapy drug. And this is very important because immunotherapy right now is given at the next stage, like chemotherapy, radiation therapy, immunotherapy. Right. It is very interesting for people who really want to understand how cancer works and what kind of therapies are there. Learn what is chemotherapy, what is the side effect of chemotherapy, what is radiation therapy, what are the side effects of radiation therapy, what is immunotherapy that we discussed, what are the side effects of immunotherapy. Now, the point is when you do research on immunotherapy, you will see that 68% of patients responds well, 32% does not respond well. So, why 32% are not responding well when already these are FDA approved drugs? So, can we design a device that can be used in a fashion that we just discussed? So, again, to claim something we should have very strong data, right. So, this is another area which people are working on, right, and I am just talking about a subdivision of immunotherapy. Immunotherapy is vast area, any therapy is always vast, right. We have to understand a small portion and try to solve that portion, try to understand further. So, as an engineer I can only I know what are the problems, but the point is I do not know lot of medical terms, And that is why very important thing is, whenever you guys design, whenever you guys develop any device, always have a clinician as your partner, right, because doctors are the right person to talk to if you want to work in the area of clinical research. As an engineer or scientist, you can help them to solve the problem. What is a problem and is it really a problem? After we do our study, we talk to the clinician, we get the response from them, we understand the problem, and then you develop your device, then you design your device, then you perform your experiment, then you show the data, and then the device will be actually useful. So, that is how you generally work in the area of biomedical or clinical research. Okay. So, point was, can you design this device, and the answer is yes, and we will see how we can design such a devices. And again, this is microfluidics. So, we call it as a microfluidic chip, all right. Okay. So, there are two more devices after this, and we will discuss this in our third module. 2 or 3 devices left to show it to you in terms of microengineering devices, and that will finish our lecture 1. After that, we will start understanding technologies to fabricate microsensors and micro engineering devices, or microsensors or MEMS based sensors, right, and we will see how we can fabricate those devices. So, we have to understand process flow, we have to understand recipe, right. It is very simple. Let us see, microtechnology also relies on process flow, it also relies on recipe, like our life, right. For example, if you want to make a sambar, if you make a sambar, right, sambar with idli, sambar with dosa, right, sambar with rice, sambar tastes delicious, right. So, the process flow to make the sambar is known, I also know, you also probably know, right, but the recipe that we use, the way I will make my sambar will be different than yours, and probably the way that our grandmother used to make a sambar will be more delicious compared to what we will make, right, because they know correct recipe. Process flow is same, recipe is correct. Same way, when you want to fabricate a device, first is you should understand process flow. What is my first process? I should take a silicon wafer. What is the next process? I should clean my silicon wafer. What is the next process, right? The process flow we know. I should etch this metal. How much time? What should be the thickness? What should be the bonding time? How can I mix my PDMS with my hardener? These are all recipes. If we do not know correct recipe, your device will not be working, right. So, it is very important that you correlate the things in your life with research. It is easier to understand process flow, and it is actually called recipe, guys. In microengineering, these are called recipes, and the process flow, same thing like our life, same thing like cooking, right. So, just understand and merge both the real life applications with the academics, and your research, your study will become easier. Okay. So, with that, just go through all the things that we discussed today, and we will discuss remaining devices in the next module. Till then, you take care. Bye.